my screen. So hello again, and sorry for the difficulties, technical and problems we have experienced, but well, this can happen sometimes with this remote mode. Not everywhere is stable internet, and that's why it's important to at least make good records which you will be able to play back later. And well, okay then. So for the practical part of the course project, let me also open the course project task. Each of you have specified parameters of the code. Today we are discussing group codes. Yes, cyclic codes will be discussed in 2 weeks. So for group code, you have only one parameter, the code word length. So some of you have 29, some of you have 31, some of you have 17. Yes, it doesn't really change very much, but still you will have to make your own set of equations in each particular case. So let's see how do we solve the task. Let us see the task itself first. So we need to do the following task. First, we need to actually design a code, yes, to have equations. Next, we need to encode code word. So perform encoding, then we perform decoding without errors, so no errors introduced, and we decode. So the syndrome should be 0. That's what's expected. Then we decode after adding one error. Then last thing, we decode after introducing double error, because it still can happen. 2 errors are also possible, and we need to know what happens in that case. Yes. So for that reason, we should test it. Yes, so that's what we are going to do. So, and we start with, as Mr. Chen started explaining to you, by calculating the number of control symbols of check bits, which we need for our M code. So this operator denotes a rounding operator towards the largest integer. Yes, so basically this in MATLAB or Octave is called cell function. And accordingly, once you calculate the number of correction bits according to this formula by substituting your parameter m, which is individual for each of you, you find out the number of control bits, and accordingly you can find number of information bits, k. Next step is actually designing the code. So we have discussed that during the lecture, but I will again go briefly through it. We start by writing down the table of all possible error vectors, starting with the error in most significant bit, first one, yes, and gradually going to the least significant bit. So basically what we have here is I matrix with the dimensions m by m. And we assign syndromes with a total number of digits r, which you have calculated. So in my case, it's 3 digits per syndrome. And we just go them through natural order, starting from 1 and ending by m. Yes, so basically 1, 2, 3, 4, 5, 6, 7, 8, 9, and so forth in binary form. That's how we assign the syndromes. Next, we are going to use each column of this syndrome to make our equation. So if you have r equal to 5, then you will have 5 equations. Yes. So each of the equations is formed by looking up which symbols have 1 at the specific column. So in the first column, only symbols E3, C2, C3, and C4 have symbol 1. So they are merged together into the same equation. So basically, this is our first equation. Similarly, we make all the other equations. And even if you have systematic code, these steps are still the same. Yes, what will be different is this code word after encoding, but so far up to these equations, you are working with non-systematic code regardless of what you have written here. So even if you have, for example, let us see, group systematic code, yes. For some reason I cannot see here. It's probably older version of the file, but okay. I'll wait. We need to actually check this. Do you have these parameters signed? Yes, we have them. So it's okay. It's some of my older versions of the file which I have opened. So for group code systematic, you still start to design non-systematic equations. So you take M27, you design exactly same way this table, exactly same way you design 5 equations, and only then you start working with matrix to make it systematic or non-systematic. Yes, so that is here where the difference starts. So we can make encoding matrix, and actually let us do so. I will make a new program to show you how it's working. Yes. So basically, I'm going to save it. That would be group non-systematic. Clear everything. And we need to input this matrix. So again, this matrix is designed by using these equations. So this is the first, the third equation, E3 equations. This is E2 equation. And this is E1 equation. Yes, and accordingly, we put them in columns. So here we have E1 equation, E2 equation, E3 equation. All the other parts are accordingly identity matrix. Yes. So I don't know. Do we have? Maybe let us show you some other example. So the minimum value M looks like is 15 for you. Okay, then let me take M equal to 10 and show you this process, well, from scratch. Yes, so basically this is one example, and I'm going to show you one more example. So if I'm going to take...
Excuse me, sir.
Yes.
Where we can have the document, the for document. Yeah, the last document you show, this one. Where we can find him?
It's here in course project part. Yes, tasks and guidelines. So this contains all your parameters. Now they are appeared.
I know. I don't have.
You are from, well, let us see. It's not really showing that you are connected. It should show here that you are online, but I cannot see you are online for some reason. Are you in this year?
No, not now.
Then probably... Okay, then after this lecture, I'm going to add you to this course, so you will have it available for you.
Okay, thank you.
Okay, thank you for asking. That's important. So yes, I will add you and you will see it. And if you don't, then please email me. So, okay, then now I'm going to make M equal 10 example. So for that reason, we start with calculating number of the control bits, which would be log2 of the M plus 1, which is, after rounding, 4. Yes. Then I find number of information bits, which is M minus R, which is 6. And then I'm going to make table of the error vectors. So I need table 10 by 2 columns and 10 rows. Yes, so starting with this error vector, which has 10 symbols. Yes, so that's 8. And this would be 10. Okay. Well, it will take a little time, but I'd like to show you complete example so that you understand everything what's happening step by step. Okay. Accordingly, if you have m equal to 31, then you have to make this big table with 31 row, and your matrix will also be quite big. So, yes, it's faster like this. And in the second column, I'm assigning some syndromes. The syndrome is consisting of 4 binary symbols for me, and we start with syndrome 1 and go into the natural order up to number 10. Yes, you have a question? Sorry, can't hear you. Well, if you have questions, please ask. Don't hesitate. I'm glad to answer. So this is 1, 2, 3, 4, and so forth in natural order up to total last number, which is 10. So that would be this, and finally 10. Okay, now we can make encoding equations. For that reason, I'm going to actually add extra column here. Insert column to the left. Here we have E1, E2, control symbols, then information symbol, control symbol, information symbol, information, control at the position of where we have only one symbol 1 in the syndrome, yes, so that would be E4, C5, and C6, yes. So basically, that is our mapping. Now we can write equations. So first equation calculates E4 by adding up C5 and C6. So I'm also going to share this file after we finish in Ortus. So that would be E4 equal to C5. Let me find XOR operator. So basically operators and yes, this XOR 5 and C6. That is first equation. Next equation would be E3, second column. Yes, E3, which has C2, C3, C4, and that's it. Yes, 2, C3, 44, but 4. So this is second equation. Next equation would be, E2, which accordingly is made by this column. That would be E2 equal to C1, C3, C4, and C6. That would be C1, C3, C4, and C6. And the last equation calculates E1 as a superposition of symbols C1, C2, C4. So I'm going to write them down. C2, C, then C5, and that's it. Yes, so we have these equations now, and we can also make a matrix. So for matrix, we have 6 information symbols, so our matrix will have 6 rows. Yes, so we have number of rows equal to number of information symbols k, and number of columns equal to m. So the matrix dimensions would be number of columns 10 and number of rows 6. Yes, and accordingly, now I'm going to put the first column as this E1. Yes, so I have C1. That would be first, yes, first columns. That would be 1. C2, I have it. C3, I don't have C3. C4, I have it. C5, and I don't have C6. Yes, that would be first column of the matrix. Second column is second equation. So I have C1, I don't have C2, I have C3, I have C4, don't have C5, and I have C6. That is second column. Next is E3, which is located at the column number 4, which has doesn't have E1, which has C2, C3, C4, and others are not present. And the last column of control bits is E4, which is located at the position 8, which has only C5 and C6. So I have basically shown you how to design this matrix from scratch for any code word length. So basically, you can repeat this process for your own m value. As for this part, this is basically diagonal matrix, I matrix, and all the other positions are filled with zeros. Yes. So I'm going to make this more compact, center, and this is our encoding matrix for m equal 10 non-systematic group code. So that's how it's designed, yes. Set of decoding equations is rather simple and straightforward. We use the same equation as encoding plus the correction symbol, and that is equal to syndrome. Please note, however, that syndrome first relies on calculating E3. That is happening because actually our syndrome starts numbering from here as 1, and in the first column what we have is actually E3 control symbol, yes, in first column. And in third column, we actually have E1. So please pay attention to this part. But other than that, these equations are also pretty simple to make. And similarly, decoding matrix is also very simple. Well, I'm not going to repeat it, but because I already have this matrix here. Yes, basically, that is decoding matrix. So what we are going to do now is actually try and input this matrix. So I'm going to create this matrix, encoding matrix, in Octave here by specifying each line of this matrix. So I'm going to use this matrix, yes, but you can repeat the same process for any other, including this one. So basically I have this row. Sorry, I need Octave. I need to put spaces in between. Semicolon. Next line. Next row of the matrix. You can, of course, write down this all in single line, but I find it more convenient to look at if you actually format it in the shape of a matrix in your code as well. This is easier to see it. Yes, it's extra space. So no semicolon here because this was last row. and semicolon here to suppress the output. I can actually disable it. We can run the code, and you can see that this is our encoding matrix. Similarly, I'm going to input decoding matrix. This is easier. I can recall it from memory, because this is just a natural numbering order going from 0 to 7 in binary form. 110 and 1111. Well, actually, it's not really decoding matrix, it's a syndrome matrix. Yes, because decoding expects also to make correction if we have error. However, as you can see, we don't write right now this code capable of making the correction. It only will tell us what is the syndrome, and that is all. So, in order to go further, you will need some data. For data, you can use your name, surname, yes, considering, for example, these sounds like E, A, O, and so forth. Don't recall how they are called in English, unfortunately, as ones, and accordingly other sounds, L, N, S, and so forth, as zeros. So pretty straightforward. And you repeat your name, surname as long as you need to get actual K number of bits. So for my case, I only take first 4 symbols, but if I would have K equal to 10, then I would need to actually go this way. For K equal to 20, I would need all of them, yes? So you just repeat your name, surname, and that generates your data you will be checking. So my data is 1010. That's actually where this data comes from. In example, we have been looking. So data is also a vector, raw vector, 1010. Now we can make encoding by putting in this data into the equations, right? Or alternatively, by calculating matrix multiplication. So now we calculate code word. Oh, sorry, let's see style. Code word. So that would be cd vrd. We multiply data with encoding matrix. And don't forget that you need to actually calculate modulus 2. I think there is such operation octave mod 2, yes, to find a reminder. Okay, then let us run the code, and you can see that our code word is 101010, which is correct, right? Now, for decoding, we have multiple cases which we need to consider. Some free spaces here. I understand now why I didn't see anything. So the tasks were to check for errors if your message doesn't contain error, yes, without introduced error, check after adding a 1 error, and check after adding 2 errors. So let us start with a case no errors. Yes, so then syndrome is calculated in a similar way. Synval will be code word multiplied by syndrome matrix and reminder 2. Yes. Or alternatively, you can put all the values inside this equation, add everything together, and get the syndrome. So it should be 0 if we didn't do any errors. Operator non-confirmed, sorry. Syndrome matrix. Yes. We shouldn't write this syndrome here. Yes, we should start from 1 and go to 7, not from 0. 0 is syndrome when no errors. And accordingly, we don't do anything if we know there are no errors. So As you can see, in case of without errors, we have no syndrome. So we can actually even add here fprintf, no errors scenario, just to add some information. Fprintf for the word. Well, I believe this. Yes, I believe this even not necessary, so that we will be seeing everything in one line. No. Well, then let us put it back. Some error fprintf. So this is similar to printf function from C programming language. Yes, so no error scenario. Now we need accordingly one error. Fprintf one error scenario. And similarly, two errors case, right? To see what happens then. Because for one error, it's expected that it will find correctly the position of error. But what will happen if we have two errors? That is a question, yes? So we introduced error here in the symbol 7. So we can do that by actually inverting symbol at the position 7. So code word 7, or not 7, but 6, right? This is 6 position. Will be inverse code word 6. So after this operation, our code word is having an error. Having an error in the position 6, right here you can see it. Yes, 1 and 0. The only thing that confuses me is why it's because first I output this and then text. I need to do it in separate order, right? Then we calculate syndrome again in the same way, and the syndrome should be 6, right? So here we have done it, and that is syndrome indeed 6. 1, 1, 0. So let's see if the code gives us the same syndrome. So yes, syndrome is 110, and the error has been correctly found. So we know that we can invert the symbol, and accordingly the error will be corrected. Now, what will happen if we add double error? So in addition to already existing error in the 6th position, we add one more error at the position 3. So we're doing the same thing. Basically, I just copy this and say that I'm introducing one more error in addition to that what was in 3rd position, and try to decode now. What it says is that it found error in the symbol position 5. Let us see the table and check if it's correct or not. So it has discovered that there is one error in this position. So for us, this means that if we allow it, the code will convert this 0 into 1, and therefore, comparing to the original code word, we will now have not 2 errors, but 3 errors. So the code cannot correctly work if there are 2 errors. That is a very important thing to understand. Yes. Furthermore, it is possible to predict which symbol will be as a symbol with error, knowing where the errors have happened. So the error has happened here in the symbol 6 and here in the symbol 3. So we take syndromes for 6 or for 3 and for 6, add them together, and what we get is a syndrome which will be found. This is linearity property of the group code. Yes, so basically it will always try to correct the wrong symbol. It will never correct any of these two symbols because no way you can add two numbers, non-zero numbers, and get as a result one of them. Yes, you will always get something different than these two components. So unfortunately, it's unable to correct two errors. Even more so, I will now show you example that we will have 3 errors. Yes, so I'm going to copy this. 3 errors. You don't have to do that in your course project, but you are welcome to try if you want. So I'm going to introduce the error in the position 5. I will explain now why exactly in 5, but the thing is that it says no errors. Yes, so we in reality we have made 3 errors, but it couldn't find 3 errors. That is because one allowed code word, this one, was converted into another allowed code word. As you recall, Hamming distance, code distance, that would be, yeah, the code for Hamming code was 3. That means that allowed combinations should be different in at least 3 symbols, which is valid. Yes, these two combinations are indeed different in 3 symbols. Therefore, they are considered both allowed. Yes, you can always find, well, it's worth to mention that not for any combination of 3 errors it is 0. So you need to select only those syndromes that will give total 0 if you add them up. Yes, so for example, this will also give total 0 syndrome. However, if we add these, and these, the total syndrome will be 6, and accordingly, code will try to correct this symbol by introducing the 4th. So it can miss 3 errors. It will always find 2 errors, but will consider it as 1 and try to correct it incorrectly. And it will always correctly work with 1 error. So that is something that needs to be considered when you choose the code, right? So this is your task to make this actually and show it, yes. For systematic group coding, everything happens exactly the same. So you start with the same table, yes, and you arrange symbols here in non-systematic order, still non-systematic, yes. That's important. Now, your code word after all the things will be systematic, but in this table, it's still non-systematic, right? Then you write equations exactly the same as you would in previous case. So this is no different from previous slide, but your code word is designed in a systematic way. So what you do is you, again, select your data, yes, calculate the syndrome from these equations, then you have your data, and here you have your syndrome, which is appended at the end. For matrix part, it's the same. Yes, you literally just place the E3 where it belongs here, E2 where it belongs, E1 where it belongs, and fill the remaining part with the I matrix. Yes, so that's how coding matrix made. Yes, so in fact, I'm going to save a copy, save file as systematic. I'm going to change this matrix. So I think it's easier for me to write it from scratch. 0, 1, 0, 0, 1, 0, 1. In your course project, you don't need to consider both systematic and non-systematic. You only do what is given to you. Yes, I'm just showing you examples of both cases. So this is matrix for systematic code. And similarly, we need to rearrange our syndrome matrix as well. So I'm removing these two syndromes, this syndrome, and now they are appended at the end of the matrix. So here is, yes, well, basically you can say that this is actually reverse I matrix, yes. It's not on the main diagonal, but it's on the secondary diagonal, yes. So now everything is working, yes, so let's see. Again, you can always put all the values inside these equations and calculate, or you can write down matrices, launch Octave, and let it calculate for you. So let us make this systematic code word. Run the code. And here you can see this systematic code word, yes, data block and control. Okay, next thing that bothers me is why here we have non-zero. Then something is wrong. The code word is correct, yes, so that means that something is wrong here. So that would be E1. That would be E2, E3. Seven symbols by column. That would be decoding C1, C2, C3, E1. Yes. That would be E1, C1, C2, C. Wait, C2, C3. Wait a minute, something is. Wait, I need to see syndrome 1, which is first column. That should be C2, C3, 2, 3, 4, and E3. That is correct. Next column is C1, C3, C4, E2, and the last column is C1, C2, C4. I can see error here. Here is incorrect. Yes, it should be 0. It should be 0. So I have made a mistake, and therefore the syndrome wasn't 0. Yes, now syndrome is 0 because we didn't introduce any errors. Now we introduced error in the symbol number 6 in the same position. However, now in the 6th position we have symbol E2, right? So the syndrome shows us that the error is in the second symbol, which is for non-systematic code true. Yes, but for systematic code, it's actually here. So we need a special map to remap all the codes symbols from non-systematic code to systematic, but we will not make such map now because we don't really need it. You only need to obtain correct syndrome, and that is indeed syndrome of one error. And of course, the problem stays. If you have 2 errors, you are still getting syndrome pointing to incorrect position. Yes. And if you have 3 errors, well, in this case, we need to choose other 3 errors. Yes. For systematic code, that would be 1, 2. So I'm trying to figure out with which third syndrome I need to add these 2 to get all zeros. Yes. So basically, I need these 3 syndromes. Yes. And I'm going to get total 0. So, okay, that would be changing code here. First error in the symbol 1, second error in the symbol 2, and the third error in the symbol 3. So now the syndrome in this case should be zeros. Yes, so as before, systematic code can also miss triple error. That is unfortunately unaffected by whether code is systematic or not. So this is for your calculations. Yes, and accordingly, the remaining part is schematics. Well, for schematics, I have provided you with these guidelines, which you can try and follow. So let me actually show it. I open KiCad. I make a new schematic. Yes, and then following these guidelines, you can actually, it's in Chrome, sorry. You can actually design your own schematic. So you need to choose library browser. But again, you can draw this picture by your hand on paper and scan or make photo of it. It on the first launch, it opens up, and then you need to find the component you are wishing to place. So we start with register. Yes, so let's see what registers are available to us. Register. So as I said, we have 4-bit registers, we have 8-bit registers. We don't need shift register. We even have 6-bit registers. Yes, and 16. No, it's not. It's not register 16. It's something a little bit different. So basically, yes, either 6 or 4 or 8, and you can combine them to make any length you need. So in my case, I needed one 4-bit. I place it at the here. It has direct and inverse outputs. We are not going to use inverse outputs, so you already can mark them with these symbols. Or wait, rather than that, you can actually do it in the software. Yes, so this will not be connected to anywhere, and this is where our information symbols come in, come out. So the next is bus, to which we are going to connect our symbols. Yes, sorry, I should have pressed enter, I believe. No, you need to open context menu and select bus end. Yes, so that it stops, and then you can connect to this bus. It's always under this. Well, it's not necessarily to draw like this. You can always connect with simple line. Yes, you just need to press start and end, then wire end. Yes, then you need to put all the numbers yourself. Yes, so this will be, for example, first input, and so forth, so forth. So that is for input register. Next, we are going to need some XOR components. So you again place this, find XOR component, and you can select any of these. You can see that actually there are 5 pieces in one microchip. Yes, but you can choose any one and just clone it. Yes, so you can copy it. Wait a minute, it should be possible. Wait a minute, I believe you can actually place multiple. No, you can't place multiple, but you can really fast place them. So unit B will have different numbers of the outputs of terminals of a microchip. Yes, you can see first, second, third, fourth, fifth, sixth, but this is related to the physical properties of the microchip, which has multiple inputs, outputs. So what you need to do is to implement the equation. Yes, well, basically you can follow these guidelines. It explains everything, how to do this, yes. These equations, which you will have your own equations. So these two XOR components accordingly add up C1 plus C2, and the next one additionally adds C4. So if, for example, you need to add, let us say, 5 numbers, then you can always do it like this. So you connect this, you place extra, for example, C. Well, there are multiple options. You can also, of course, yes, you can also, of course, add it here. One more, yes. And draw lines, for example. Yes, so this way you will have XOR for 5 elements just by cascading them. And lastly, for decoder, we also needed line decoder component, yes. So which is called accordingly exactly same it's called. So you type in decoder, yes, and you can find here 1 to 2 lines decoder, 2 to 4 lines decoder, 3 to 8 lines decoder, 4 to 10 lines, which is basically binary decimal conversion, which not really convenient for us. It's better for us to use either 4 to 16 or 3 to 8, yes, and 2 to 4 lines, which are 2 components in the same microchip, yes. So again, you will need to spend some time working on this, but if you will have any questions or problems, you are always welcome to ask me by email, or if it's more convenient, we can also have some consultation in Teams as well. It's not a problem at all. So please don't be alarmed that you are something is not working for you and you don't know what to do. Then you can always ask me and I will be able to help you. Also, you can ask Mr. Chen as well. I'm sure he will also be glad to help you as well. So are there any questions left?
Excuse me?
Yes, sir, please.
Yes.
Do you hear me well?
Yes.
I wanted to know when is the last course planned to actually.
Let us see. So now we have lecture number 9. Let me check how many there are in total from previous year. So we'll have 1, 2, 4 more. Yes, 4 more. That basically means this is skipped. 1, 2, 3, and that gives us 16 December. Probably will be last one. Yes.
Okay, so this course ends in 16 of December.
Lectures end in yes.
Okay.
In this date, but the deadline is January for all your work. So you will still have some time after the course to do everything.
Okay, but the things I wanted to know is I'm planning to come back in France.
It's not a problem because everything can be sent by email. Yes, and basically this course is designed taking into consideration this COVID situation and so forth. So everything can be done remotely.
Okay, great. So there is like no problem to come back in France, right?
Yes, absolutely
Okay.
no problem.
Okay, great. Thanks.
Excuse me, sir. I have
Yes.
other questions. In Artus, we don't have the lectures, the record of lectures.
Yes. Yes, I will correct that because, well, a lot of things have been going for me, a lot of reports, some personal problems in life, and well, I just
Yes,
didn't have time. But
it's normal.
I will put them. In the meantime, you can always watch from previous year. This is channel, yes, and all of the records according in the same order, yes, are available. For example, today we had group Encode, and you can see all of them from previous year as well, if you need them right now. Yes, but I will upload them today. I already have downloaded them from Teams, so now I only need to upload them to YouTube, and that links here.
Okay, thank you.
Okay, so you have now access to Ortus, yes, and you can see these old documents. This one as well, yes. Okay, then. Thank you for your attention, for your questions, and wish you nice weekend, nice holiday. Next week we don't have lecture, but I again will notify you again in the Ortus so that you all are aware of this. And thank you, and wish you nice day. Goodbye.